thank you for the kind introduction, and thank you for hosting me. I got to see the Natural Museum, Florida National Museum today, and that was wonderful. And the butterflies, so wonderful. And it's great to kind of be back in my home state. I actually grew up in Florida, Miami, and graduated from Clearwater High. And my sister, who reminds me constantly when your team's doing well, that she went to the University of Florida. And I told her one time when I was at a fancy French restaurant in Paris that I ate gator once. So go ahead and eat my mascot. But I'm going to talk about geotechnical extremes reconnaissance. I think this is a key element in reconnaissance. We learn so much from nature. It's terrible that disasters occur. It would be equally terrible if we didn't learn from them. And so the tagline for GEAR, which is supported by the NSF, is turning disaster into knowledge, taking advantage of these observations to move us forward. As you know from living in Florida, in fact, when I remember, I think it was 1968, 3 hurricanes came over Miami at that time. In fact, one of them, the eye went over our house. So my dad and mother allowed us to get out for 10 minutes and just see what it was like to be in the eye of a hurricane. So I understand how big the threat is, but you have specialists here, people that have worked on several earthquake reconnaissance. One of the more recent ones that GEAR looked at was the 2022 Hurricane Ian and the damage done at Fort Myers Beach, for example. My latest earthquake, and I do natural disasters, but I focus more on earthquakes. I've been doing this for about 35 years, was the 2023 magnitude 7.8 Turkey earthquake. And there's nothing more devastating than to see a collapsed structures like this. And this is a picture taken from that same city about 2 months after the earthquake, where buildings were being torn down, and you realize each footprint of that building killed people. And the official toll of death from this earthquake is 50,000. 50,000 people never die. Even numbers don't die. Anytime you see a number that's 50,000, you know it was more than that. In fact, I think in this city alone of Antakya, there was at least 50,000 people who died. So a terrible event. We saw things that are reminiscent of what we've seen from previous earthquakes, whether it's 64 Nagata in Japan, or whether it's a 1999 Kocaeli earthquake in Turkey. We're losing support, buildings tipping over, buildings settling excessively here. But we saw additional things. The beautiful city of Iskenderun, a coastal city, had very few times where it was flooded. But because of the earthquake causing settlement and the movement out to the sea and the loss of ground because of that as well, they had frequent flooding after the earthquake. This is just one of the floods that actually disrupted our reconnaissance effort, because the water started coming in, and we started talking to a person who was living there and says, oh, this happens 2 or 3 times a month now since the earthquake. And so how do you rebuild a city without putting essentially a large seawall around the outside of it that blocks the beautiful vision of the ocean or the sea when you have this kind of issue? And so sustainability has to include resilience, which has to think about natural disasters. The geotechnical engineering field, as those of you that are in it realize, it's a very experienced field. I mean, from looking at Terzaghi and Peck and the late Professor Harry Seed as well, case histories are really the cornerstone of our profession. We learn so much from case histories because we simply cannot replicate in the laboratory or on the computer soil deposits that have been aged for thousands of years. And so field observations shape our understanding, and they provide the data that really form the empirical designs. And you know, Darcy's law is an empirical rule. I often get people say theory surpasses all. Well, no, empiricism is important, and if it's well done, it can lead to great breakthroughs. So for example, liquefaction, whether liquefaction occurs or not, and many of the consequences of liquefaction are based on field case histories where liquefaction was observed or not liquefied. And that's far better than a 40-parameter constitutive model for predicting the triggering of liquefaction. We focused on earthquake engineering In fact, it's blocked here by this thing, but originally GEAR was Geotechnical Earthquake Engineering Reconnaissance. It was Katrina, and this is the LiDAR image that was shot of the eye wall that got twisted on the 9th Ward. We realized the same post-event reconnaissance we were doing for earthquakes in terms of capturing what happened when the ground deformed and its impact on infrastructure could be used for hurricanes as well, and floods and landslides and other natural disasters. And so we retooled our name and said, okay, we're still GEAR, but now we're Geotechnical Extreme Events Reconnaissance. Let me see if I can move this to an area that's less disruptive. Yeah. But it's personal. This is the route I took home in 1989 on October 17th to watch the Bay Series, baseball, World Series. San Francisco Giants playing the Oakland A's. How often do you have neighboring ball clubs playing each other? And so I, like many people, cheated and got home early. So I was in front of my television set in my apartment in Oakland at 5:02 p.m. on that Tuesday, when it occurred. If not, I probably would have been one of the people going home through the Cypress structure, which at 5 p.m. until 6 was essentially a parking lot where cars were backed up. There wasn't much traffic on that day because most people did what I did and got home early to watch this baseball game. And that saved a lot of lives. Not enough, because 42 people still perished because of the collapse of the Cypress structure. But it could have been much worse if it was a normal Tuesday when we didn't have the World Series in our backyard. And you can see, and the structural engineers will talk about the non-ductile columns, and these are key issues in terms of structural engineering performance. But I think it's important to look at the fact that part of it collapsed, but part of it did not collapse. Same badly built structure, shaken by an earthquake 70 to 80 kilometers away, part of it collapsed, part of it did not collapse. You go back to the old maps, people liked Oakland, and so they initially developed Oakland in the stiff high ground, but they liked it so much they started filling in the marshes on top of the soft clay and built the city out. And you can see the fill area, so liquefiable soils on top of soft clay, that's the section of the Cypress structure that failed. So the foundation critically affects the performance of the structure. Another reminder of that, you can see the amplification of the low intensity motion on the soft mud versus the sand and gravel, which was stiffer. And in fact, when I was listening on my radio after the earthquake, I had heard the Bay Bridge collapsed. Fortunately, only one section fell down, but that's another important issue. It costs nearly several $1 billion to essentially fix this bridge and put a replacement in there, and a person died. But there are a lot of other bridge structures. I was trained to do reconnaissance in the military. I was a Corps of Engineer officer. I served in Korea for 2.5 years, and much of my mission was reconnaissance. So I had a natural feeling of essentially getting on to bridge sites and being able to do reconnaissance, understanding roads and geology and those kinds of things. One thing I learned, though, I learned from my family of 9 kids and my parents, is never ask for permission. Everyone was sent to this bridge site, and they all asked the police officers that were guarding the bridge, can I access the site? And the answer was no. I showed up in my military uniform because I was still in the reserves. And I said, I'm here to see the bridge. They just passed me right through. And so I was able to capture this response. So better to ask for forgiveness than ask for permission. The damage in San Francisco was severe. These are 4-story buildings. You can see the soft story collapse. And so there were issues, but there were more damage in the soil sites than there were on the rock sites. So Presidio itself, the old fort, is a rock site. There was a fire that was initiated by the liquefaction, and there was no ability to put the fire out because of the liquefaction breaking the water lines. So they were trying to pump water out of the bay to put this fire out. The fire marshal says he would not have fought that fire at the source if it was a typical day in San Francisco. If you want to fly a kite in the Bay Area, you go to the Marina District. All but 8 days a year, the wind blows steadily. That's the place to fly a kite. This happened to be one of those 8 days where there was no wind. If there was wind, this fire would have spread, and this fire captain would have moved back to Van Ness. Anyone who knows San Francisco, that's some distance to get a wide enough fire break, a wide enough road to fight this fire. Fire is called a secondary factor. It is the primary factor when you think about death and destruction. When I first went to San Francisco, I talked to elderly people in the 80s that were young people, 8 to 12, when the 1906 earthquake occurred. And they always corrected me. Said, you mean the 1906 fire? They called it the San Francisco fire because it's the fire that devastated the city. It's the fire that killed so many people. The earthquake may have initiated it and made fighting it difficult, but it was the fire that devastated it. And you think about Katrina, it wasn't really the wind, and it really wasn't that aspect of the hurricane. It was the surge, and it was the flooding that basically caused the death and destruction. It's amazing to walk through New Orleans, a place I had been several times, and just seeing a water line on every building and realize every one of these people had to be displaced, and how are they going to move back in? Then we had the 1994 Northridge earthquake. The United Nations had declared that 1990s was going to be the decade that reduced the harm due to natural disasters. Well, nature doesn't listen to the United Nations. And we had another earthquake. And much like the 71 San Fernando earthquake, there was devastating effects because of ground shaking on transportation and buildings and slope instability issues. That's one reason you can get a low rent, but that's not necessarily what you want to drive rents down in LA. 57 people were killed. Only 57, too many, but it was Martin Luther King, Monday, holiday, at 10 o'clock in the morning. If it had been later, 5 o'clock in the morning, if it had been later in the day, the shopping malls and a lot of the garages that collapsed would have been full with people. So we've had 2 warning shots where too many people died, but it could have been much worse. The Santa Monica Freeway was the busiest freeway in the US at the time this earthquake occurred. One section, there's overpass after overpass after overpass. One of the overpasses collapsed. Why? The structural systems are the same. Anyone who understands Spanish, La Ciénaga, the swamp, okay, there was a softer soil. When we took the time and investigated it, this is where the soils are softer. So this continuing theme of soft soils amplifying shaking, causing ground deformations, leading to damage. The scariest thing after the earthquake is what they found in the storage facility. They found RPGs, claymore mines, grenades. So I don't know what people are preparing for in Los Angeles, but that scares me more than an earthquake. We had several Japanese investigators come to Northridge and Loma Prieta and said, this is never going to happen in Japan. Japan is one of the world-class countries when it comes to earthquakes. And they normally were focused on the 1923 Kanto earthquake, where under Tokyo, they had a major earthquake offshore, and it devastated the area. It led to a fire, and it killed too many people, over 100,000. And most of the earthquakes since then that had developed their concepts of earthquake engineering were all offshore. It shakes for a longer time, but it's not a high intensity shake. This was a forward directivity shake that just hit with 1 or 2 big pulses and caused most of the damage. My brothers used to play a cruel game called Slip the Rug. I'd stand on the rug and they would pull the rug out from me, literally, and I'd fall down to the ground. That's what older brothers do to teach you about life, okay? This is kind of a slip the rug. The ground moved a meter in this direction and a meter back. Well, when it was moving a meter to the left, the bridge has mass, has inertia, wants to stay still. That puts tremendous demands on the columns, and that's what led to that failure. So ground pulses and near fault ground shaking, things we didn't even talk about in the 80s and the early 90s, now we realize we have to design for ground shaking in the near fault area. 6,434 people were killed in a country that has some of the very best earthquake engineers in the world. This is what that pulse felt like. You can see the time on the clock. It starts off at about 20 seconds, 21 seconds, 22 seconds, 23, 24. It's essentially not ground shaking over a long duration at a moderate level. It's one or two pulses. And if you can survive those, you can survive. Your building can survive. And so much of earthquake engineering had focused on ground shaking from afar. Now we had this new thing called near fault forward directivity, transient ground pulse that we had to be able to withstand. But the most devastating thing actually was the fire. I remember going to this area and seeing a young woman put flowers next to the pictures of her parents who lived in the house, and it touches you. I mean, it's terrible to see a disaster, and you have to be mentally ready for it, but people die. And think about Kobe, 1.5 million people, 6,400 people died. Kenichi Soga was actually a graduate student at the time, and he came with us and he interpreted. No one we talked to had not experienced death. They either lost a family member, a classmate, an uncle, a niece, and then you realize any death has terrible consequences, but 6,400 is unforgivable. We've got to do better than that. I went as a young man, I was young at that time, and I just couldn't believe. I mean, major steel structures like this, and then plastic hinges and collapse, and deformations on the order of 3 meters where the ground moves toward the sea, and all of this sand is from ejected from liquefaction. You can see the damage here in terms of the sea. 186 berths in Kobe. It was a fifth of their container traffic came through Kobe. One person understood liquefaction and actually had retrofitted it to mitigate it. And those 6 berths were the only berths that were operational after the earthquake. All the rest were gone. Well, Kobe can rebuild itself. All that container traffic goes to Osaka. Now Kobe builds a good port. How many come back? Not all of them. So they're much depressed compared to where they were before because of that. So if you want your city to be sustainable, you have to make it resilient. But I walked around there, I was completely shocked. The subway, underground structures do well during an earthquake, but not if they're in an area of near fault ground motion with some softening due to soil liquefaction. I was one of 4 people that was allowed into the subway because Professor Tom O'Rourke knew Professor Hamada, who was able to get Liam Finn and Tom O'Rourke, myself, and Kenichi Soga into this to look at this. It was amazing. It's changed the way we do tunnel design in terms of looking at racking loading and understanding tunnels can fail. But I remember being shocked and thought, okay, I have so much to learn. And I looked at the senior members of the group, Jim Mitchell and Ed Idris and John Christian, and they were as shocked as I was. And so I realized this is a field that will never not shock me. And I've got a lot of work to do. And when I start feeling confident, I'll go on an earthquake reconnaissance like 2023 to Turkey, and I'll be shocked again. So we had done those reconnaissance kind of ad hoc and done a good job. I'm proud of what we did, but we could do better. And so I actually talked to Cliff, it was Cliff Astle who talked to me and said, you know, you guys are doing a great job. I really love what you're doing, but I'm not going to be here forever funding you guys. You should set something up. And so I wrote a proposal at the time, a single PI proposal, very small amount of money, I think like $125,000 over 5 years, to establish something called something. I didn't even have a name at the time. post-earthquake reconnaissance. It became geotechnical extreme reconnaissance. One of the first things to do is, okay, let's get David Frost and J.P. Bardet and Les Youd and Ellen Rathje, and let's get this group of people together, diverse different backgrounds, senior and junior, who've done some reconnaissance, and let's create something. And we created GEAR. It was actually David Frost who came up with the tagline, turning disaster into knowledge. It was Rob Cahan's brother who made the little symbol that we had here called GEAR that we liked. But the objective was, let's collect this perishable data. Once a tractor or a dozer goes over that land, you've lost it forever. You've lost the data. Develop and implement new technologies. I remember going to Japan and getting up in a helicopter after the 1994 Kobe earthquake and seeing fault offset through a tennis court. You don't see it many times in an urban area because all the building damage hides it. But you can see surface fault rupture when it goes right through a tennis court. You got the lines there, you know exactly how much it's moved. So I said through the interpreter, do you know where that is, pilot? The pilot said, yes. So we got back and he goes, it's here. And I realized it took me hours to find out where that tennis court was. And so when we learned about GPS devices and we went to the 1999 Kocaeli earthquake in Turkey, we said, you cannot come on this reconnaissance unless you have a minimum of a Garmin 3+. And when I flew in Turkey and I saw something, I hit it with my GPS device, and I could then say, you two people with your Turkish student, you go to this GPS coordinate and you find it. So it really revolutionized the way we did earthquake reconnaissance and natural hazard reconnaissance. And one of the things is to document the geotechnical effects so that we can advance research and understanding. And not just for earthquakes, which I focus on in this talk because that's where my primary expertise is, but hurricane, surge, also landslide, all of that was captured by post-extreme events reconnaissance done by you. That's the thing. This has never been about me. It's never been about Ellen Rathje and David Frost. It's been about people who were naturally going to go anyway, but to just organize and channel that energy and do things in a more systematic way and make sure that not everyone in the world goes to the same location to see the same thing, but we basically spread people out to capture the effects of the event. Principles of reconnaissance. Safety. You have to remind people you cannot die. Rick Fergesi told me several times, I love what you're doing, but if anyone gets injured or dies, no more money, okay? Yes, so it's amazing how sometimes we'll put ourselves in because we'll be focusing on something and we won't see that there's all these boulders on the ground at this site, came up from that mountain up there. If there's an aftershock, I got a problem. You got to be able to step away. I talked about this lateral spread in Taiwan, really well done mapping, except for a big gap. I go, how did you miss this? We can't really have a first-class case history unless we have the deformations here. They said, well, there's tall grass there. I said, well, you could still see the cracks if you were careful. You go, no, John. They say they have a 3-step snake that lives in that grass in Taiwan. If it bites you, you have 3 steps before you die. I said, oh, you did the right thing. You did not die in collecting data. You have to have a team approach. There's no loose cannons. There's no all about I. This is a team approach that we have to work together. The data is created by the Earth. It's owned by the Earth. It's not owned by you. So number one thing we said, you're not putting your name on any pictures. Anyone could have taken that picture. And it's the Earth's data. And we're National Science Foundation supported by taxpayer dollars. Everything has to be given to everyone. We've got to share. And we have to be ethical. And we learned that because we mainly have ethical people, but then we had one misunderstanding and we realized, we got to step back and write an ethics guideline. You can't assume everyone is aware of all those issues. We always get an overview, assess the overall damage, identify key opportunities. And then we ask ourselves, will the documentation of these effects advance the profession? If a clean, loose sand liquefies, who cares? We know loose, clean sands liquefy. If a silty material liquefies and damages a pipeline to where it fails, that's where we focus our attention. And so you're deliberate in the limited time you have on site. And you remind yourself, 4 hours on a site to well document it, so it becomes a case history that can then be analyzed and be in a journal publication, is worth more than all the photographs in the world. The days of driving by, taking pictures, the more pictures, the better. No, fewer things done well is more important than a lot of pictures. And then take advantage of technology. You know, that's why grassroots is so important, because you learn about, someone says, oh, this thing called LIDAR. Oh, what's LIDAR? I didn't know about LIDAR, but someone came there and did structure for motion. Oh, we can do that. It's amazing how many bright young people there are. Then have a systematic, everything has to be collected with GPS, and it has to be time and date stamped. There was a controversy over this one location, which was very well described with a fence line and a road that had been offset by the Kocaeli earthquake in Turkey. But one team said it moved 4.1 meters. The other team said, I went to the exact same spot and moved 4.2 meters. And the other team, no, 4.3. Now we all have the same location, so we had the GPS. It wasn't, oh, let's look at the time. Because otherwise this is epistemic uncertainty. We'll say, oh, 4.2 plus or minus. The first team was there a week after the earthquake. The second team was there 3 weeks after the earthquake. The last team was there 2 months. It's fault creep. It's something scientific as opposed to human error. And so having the timestamp is critical. And this is the hardest thing. Engineers want to figure out what happened. And it's good to think of all possible mechanisms so that you collect all possible data to be either supportive or be against any hypothesis. But you can't just collect the data that explains what you know is what happened. You have to be back to just the facts. There's plenty of time later to get in the room with all the facts to decide why it happened. And if you bias too much, you're going to miss some important data. So this is a much younger me when I landed in Turkey. So I landed in Turkey on the big jet from the US. The first thing I did with my contact, Darren Urel, is let's get over to a airport for domestic flights where we can hire a plane, make sure that it's got the wing on the top so we can look down carefully, and let's fly over the zone. Because getting that aerial reconnaissance in the military is critical. It's really important after an extreme event to basically fly over the area. When I flew over Adapazari and I saw this, I said, there are other things to see, but this has got to be a focus because there's so much. I could see the ejector from the air and I could see all these tilted buildings. Taiwan, you cannot rent a plane in Taiwan, okay? Only helicopters. Helicopters are expensive. Back in 1999, in September, they were $3,500 an hour. Okay, I want 3 hours on this thing. So I say, hey, Les, you're harder. You work for a Department of State. You want to see this stuff. You give me an hour of money. And you have another, at PG&E, you have an hour. So now I only have to pay for 1 hour. It's still expensive. So I have a friend whose dad used to be the vice prime minister in Taiwan. And he found a helicopter company that gave us a deal. And so we got it for $2,500. That's the last time I gave the US government a deal. We flew, we got the pictures like this. This is 9.1 meters. That's a human being for scale. This has been pushed up 9.1 meters. I found out that helicopter crashed 2 weeks after we flew in it. And they did an investigation. They were not keeping proper maintenance. That's the reason why they were cheap. So lesson number one, don't ever rent the least expensive helicopter, okay? Because J.P. Bardet, Norm Abramson, Steve Kramer, and Les Harder and Jon Bray would have perished if they had flown that helicopter continuously. This is my best ride, okay? I'm in Turkey and I have contacts in the military because I served in the military. I knew the military had gone there from the news reports for a life safety mission. I knew that that was over, unfortunately, because 7 days had passed. So through my old ops officer, I found out that the Marines had the USS Kearsarge there, and they had helicopters. So I said, I'm on this National Science Foundation, very official mission. I need a helicopter to get up in the air to look over Adapazori. And they said, okay, what type of helicopter? I said, just one of those small observational helicopters. There's a Loach, there's like 2 people in it. So I had to bear it, okay, out of all the people, Ellen Rathje, you can come with me. So Ellen and I are standing there, and this helicopter starts coming, and it looks small, bigger, and then bigger, and it lands. It's a super stallion. It can actually hold a platoon of soldiers, 30-some soldiers plus a Jeep. And then I get in the helicopter, we take off. It's just Ellen and I got a Navy camera person to basically take photographs so I can get good detailed photographs. And it is actually the helicopter that landed in Bosnia that saved Captain Scott O'Grady. This was the helicopter. It's the first time I earned the respect of my son, because he was reading that book when I came back from Turkey, and I showed him this picture, and the number on it matched up to the picture in the book. He goes, oh, Dad, you actually are doing something useful. Now we can all ride, because we can all get a drone and we can fly over. We can see, if you look closely here, you should see fault rupture right there. So this South Napa had many effects, but one of the most important was fault rupture. But the idea that a gear team arrives on site, and it's so important to get that local area reconnaissance, so aerial reconnaissance. So you're not just guessing what's important. You can fly over the site, and you can not only capture information and use structure for motion to get detailed maps, you can know where to go and where not to go. And so that's the new thing in terms of using UAVs to basically see the battlefield and be able to map out a strategy for capturing the effects. That's the fault rupture right through there. And one of the incredible things is structure from motion, is being able to have controls on the ground, fly it with a drone that's geolocated, and from looking at it from different perspectives, being able to stitch together a diagram. This is from a scour event in Greece, but you could not walk on that bridge. It's unsafe to do so. You would never get those measurements, but now you have those measurements. Every pixel has good accuracy in terms of X, Y, Z. And then Diane Moog brought a LiDAR set to Turkey when we went in 2023, and we're able to capture in just about a minute something that would have taken us forever to document all the details. I mean, every one of these pixels is placed in terms of X, Y, Z with good accuracy. And we can see things like, we obviously see a little water here, and it's punched in. So you know that and you can see some warping. You can see the fence between the buildings being dragged down by the buildings. And this is something I had not seen before. And you needed the detail of LiDAR to notice that the buildings didn't just punch down like they normally do. They dragged the soil next to them. So and there's a building that was heavily damaged, a light building, where the big brother punched down, dragged the ground down, which then distorted the other structure and damaged it. So now we don't have to just worry about liquefaction effects on your building, but how it may actually cause damage around it. And that's captured very nicely in all these case histories with these LiDAR images. Remote sensing is really important. In fact, when I was in Chile, we did not know about this tailings dam failure. And in fact, we had to talk to someone. We had heard some information about that, but mine operators are not going to say, hey, by the way, world community, we had a tailings dam failure. And unfortunately, we killed 4 people. We're not going to advertise that. So a lot of tailings dam failures in the past have gone unnoticed. But now with remote sensing and satellites, you can see this. You can see what it was, a closed upstream dam that liquefied and flowed down. And so it took about 4 hours from the main highway to get to that site, but we got to that site, we were able to document that as a case history and a flow failure. Google Earth revolutionized the way we do things. When I went to Turkey in 1999, we had so much difficulty getting maps. The best maps we got were from a Russian website that, because the Cold War was over, he could sell all these topos of Turkey. I don't know why Russia cared about Turkey, a NATO ally, but we had these incredible DEMs, but we had a lot of information was missing. And in fact, the city of Adapazari, we had no map. So how are you going to map the earthquake damage when you have no base map? I went into the office of the mayor and he said, I cannot share any map. But I have my camera down here. And so I took a couple of pictures of the map behind him on the desk and then brought it out and we blew it up and that's what we used, okay? I'll admit that today, and I'll admit that only because I'm out of Turkey and they can't throw me in jail. But here's the 26 February Google Earth image that you could pull off your computer and look at the liquefaction. You can see the sand boils. You can see, unfortunately, this collapsed building. And so you hit the ground running. You already have a sense of what happened on the 22nd of February, 2011. It's good to look at what happened before the earthquake. So the 15th, you can see, for example, this building standing tall, and you can see its collapse. And so having these satellite images and being able to change detection is incredibly insightful. But then if you care about resilience and building back, you can actually keep on walking forward in the future after the earthquake or post-earthquake and see how the city is rebuilding itself. And with those longitudinal studies, the social scientists can start talking about the true impact of an earthquake. I mean, there's still buildings in Christchurch, New Zealand. I was just there in August that looked the same that they looked on February 22nd, 2011, which that's too slow a recovery. And now we have this. I was actually in Seoul, Korea when this earthquake occurred. I text Ellen Rathje at UT Austin, Design Safe. I go, hey, what do you know about this? She mines what's available on the web, and you get a sense and you realize with all these cameras we have now, you not only know that these buildings were damaged, you can actually see how the buildings were damaged. You can see the shaking induced damage, and you can see the collapse there. So we have cameras on all of these security cameras, but we also have human beings that are incredible scientific instruments who have cell phones that take pictures of this stuff. And so mining this data is an incredible opportunity to learn from. But I wanted to kind of, in the last part, is just talk through some of the earthquake reconnaissance efforts I've been on and post-earthquake or post-natural disasters, extreme events. One of them is Adapazari. I highlighted in yellow the names of all the Turkish engineers. We could not have done this without our Turkish engineers. It's so important to reach out to the country that's affected, let them grieve and let them understand that, but then have them participate so that you can capture the data. This is another earthquake where 1,700 people died. I add the plus because my military contacts who do estimates of casualties from bombing exercise in collapsed buildings said, given all the collapsed buildings and the time of day, it was far more than 17,000 people who died. Adapazari is island swamp. It's an island between two rivers. The Romans built a bridge across this river over here because 2,000 years ago, that's where the river went. And so it's a very active, think about the Mississippi River. It's a meandering river. So where the river is lying now is not where it was 500 years ago or maybe 1,000 years ago. And the classic case, this is rock, this is soil. Rock had fewer than 5% collapse. The soil had high percentages, at least 15%. In some cases, more than 45% of the buildings were damaged. So now the issue is to understand why was the damage almost 50% in some districts and only 15% in other districts. So we got with a structural engineer architect Coburn and Spencer, and they gave us a rapid survey. We could go building by building. So this is just one of the surveys where our team surveyed 60 buildings, and they recorded structural damage, no damage, architectural damage, minor structural damage, so a little bit of cracking of load-carrying members, significant damage, you have displacement across it, partial collapse or collapse. We came up with a ground deformation where there's there's no ground failure, less than 10 centimeters to 25 centimeters of settlement, and more than 25 centimeters of settlement. You collect that data. Then you always have time the next summer to go back and do cone penetration work, followed by some SPT testing with energy measurements. You collect the subsurface data. Then you do your liquefaction assessment, and you go, okay, it's not surprising. This is not supposed to liquefy, and it didn't liquefy. And the building damage, badly built buildings were still damaged on good ground, but the rate of damage was less than the buildings that were on liquefiable soils, especially if there was liquefiable soil on top of deeper liquefiable soils. But you had to make a change. The Chinese criteria, which was used in Yao et al. As the state of the art, was wrong because it looked at the percent of particles, and you can have a silt particle that is clay size, it's a silt. And that's why Casagrande didn't use size for silt and clay, he used Atterberg limits. And so an Atterberg limits or PI-based criteria better captured the data. And so those observations led to the PI-based criteria that's now used for liquefaction susceptibility. Chile in 2010, again, could not have done this without Ramon Verdugo, Christian Ledesma, and Terry Eldridge, and all these other people, and the Chilean Air Force. There's always somebody who has an uncle who knows somebody in the Chilean Air Force. They want to go fly the site. They don't really know where to fly. We go, wait, we're engineers. We can kind of tell you where to fly. So let's get together. And so we get a free flight on the Chilean Air Force to fly over the zone to capture that overview. This was the big earthquake because we didn't know the Tohoku earthquake was going to happen. We had all these kind of normal earthquakes that were relatively low magnitudes, 6.7s and 6.9s, even 7.6. This was a magnitude 8.8. So duration, we care about that for places like the Pacific Northwest, where they fear they're going to have a large magnitude subduction zone earthquake. I felt like I was doing reconnaissance for the Northern California 89 earthquake, the Southern California 1994 earthquake, and the Desert Landers 1992 earthquake all at the same time. I had done reconnaissance on those three earthquakes, and all of a sudden I land in the land of Chile, and I realized the area that's affected is hundreds of kilometers long. And so without that air reconnaissance, we could not have collected the data we collected. We needed our Chilean partners, and we needed everybody to basically download where they had been. So I got their track logs, so I could look every night on where everyone's been, where they send them out kind of orders for where they need to go the next day, because you need boots on the ground. It's another country that's dominated by ports, and so capturing liquefaction-induced lateral spreading, you can see the lateral spreading because the ground liquefies, it wants to move toward a free face. Capturing this then becomes a case history. And the lateral spreading method that we still use today is case history driven because it's too hard to do advanced numerical analysis to capture all the aspects of void redistribution and pore pressure migration with today's models. This is something I had not seen before that transportation department should care about, is liquefaction along a column. This is a sand boil. You lose the support and it basically punches down. It goes down about a half a meter to 3/4 of a meter. But it's really important to step back and not just focus on failure, but performance-based earthquake engineering demands that you look at performance of good. For example, many dams, most dams in Chile did well. But we found the one earth dam that did poorly, And this has a silty clay foundation. It's not liquefaction. It's basically spread out on top of that softened material. And then we had the tailings dam, which I showed you the remote pictures. These are the on-site pictures that were taken by the team. And it was clearly liquefaction because during one of the aftershocks, if you have an 8.8 earthquake, you're going to have magnitude 6.9 and 6.7 aftershocks. That was the Loma Prieta earthquake and the Northridge earthquake. We felt those aftershocks after the earthquake, and that tells you you can't just worry about the main shock. You got to think about the aftershocks. And if you go to a ground and you map a lateral spread, and there were significant aftershocks before you got there, how much of that ground movement was due to the main shock and how much was due to the aftershocks? And that's why you want to get there as soon as safely and appropriately. You don't want to be there when people are doing the life safety mission, but you want to be there a minute after that mission's over. And I'll end with the Canterbury earthquake sequence. And in fact, we talk about earthquake sequences. I talked about the Loma Prieta earthquake, the Northridge earthquake. Here we talk about the sequence of earthquakes. So now we don't just focus on one earthquake. We realize sometimes one earthquake puts strain on the fault that's adjacent to it, which causes another earthquake and another earthquakes. And we have to think about sequences. This had a magnitude 7.1 in September of 2010, caused liquefaction damage, nobody died. Then a magnitude 6.2. So a magnitude range smaller, but it was right next to the city. Ground motion was more intense. Unfortunately, 185 people died and more damage. Then they had the June earthquake. Then they had the December earthquake. Then they had the Valentine's earthquake. There are people that left Christchurch. It was the second largest city. It wasn't after the earthquake because people said, I'm done. I'm out of here. I was doing centrifuge tests at Davis where I would make a model. It's so expensive to make a model. I'd shake it once, shake it twice, shake it three. I left Davis because they were doing full-scale centrifuge, full-scale shaking table tests in Christchurch. That nature was. Massive liquefaction. This looks a little bit like Buffalo. So Clarkson, you should know that. This is like Buffalo after a snowstorm, okay? But it's sand. This area actually settled about a meter. There was like 30 centimeters or more of ejecta on the ground. People, when I first got to Chile, they said, don't worry about liquefaction. We have so many earthquakes. Everything's liquefied and densified. False. The places that we looked first in '89 was where there was liquefaction in '06, because the ground that liquefies is born again. It basically liquefies and it pluviates through the water. It's loose, it's fragile fabric, it's prime candidate. So what does a New Zealand geologist do when liquefaction hits his home? He goes and takes a picture and he thinks he's done. Then he has a bigger shake. So he goes back to the same location and takes a picture. There was a 4.6 aftershock. He goes to the same location and takes a picture. There was the first part of the June earthquake, a magnitude 5.2. Then the magnitude 6 occurred. So liquefaction is most likely to happen where it's happened. It's one thing when liquefaction takes your car, your ride. It's another thing when it takes your throne. And in fact, what reminded me of this was Katrina, because we think of earthquake engineering and liquefaction as being a solid mechanics problem, but I realized this was a flood event. People who had just moved back in their houses because they had damage from the September 4th, 2010 earthquake, they basically shared the holidays together. They kissed their significant other on Valentine's Day. And then 22nd of February, just a few months before, they had not only a liquefaction event, but they had a flood event. Everything on the floor was flooded. Before they buried it to build the great city of Christchurch, a geologist mapped the streams that existed in 1850. You go back to those and say, okay, these have all been covered now, because we still see the Avon River, but this has been covered. But this is probably still there, and the buried stream has now re-emerged as a liquefied sand that's leading to more damage. And I found a book called Christchurch, Swamp to City. And it was interesting to see how that city had been developed over those years. This building, I used levels. Now we maybe use LiDAR, but at that time I didn't have access to LiDAR, but a couple of people with a team with proper laser levels and such can do a detailed survey. This building had not settled. There was a pipe that was detached, so we had a very precise measurement there. That's actually from that. And then we were able to do a measurement inside this garage, the first level, and see, okay, there's about, there's 60 millimeters here, and there's 110 here, but it's very large differential settlement, about 100 millimeters extra for every 5 meter long bay. And that is where we saw ejecta. Then there's a parking lot here, so I do closely spaced CPTs, and guess what? I find a shallow buried stream. You can see the ejecta here that just cuts the southern part of that building, and that's the area that had the massive liquefaction. So look at the geology and realize streams that we have buried are going to reemerge and cause problems when there's an earthquake that causes liquefaction. This analysis now with the CPTs, we can show this buried stream channel, areas where we do not have liquefaction that's shallow. We get some liquefaction at depth, but not shallow. We can model it as a case history, which we're not going to get the right answer unless we capture that loose layer. We can capture bearing capacity. We could say that the north side is going to settle less than the south side. And we can actually get the wrong answer, because this is how much was measured. And with our uncertainty, we're getting this. And then you realize ejecta, no continuum model captures ejecta. So if we had matched it with a computer program that had a model that did not capture ejecta, we would have had the wrong answer. So then we go back and realize, let's just look at the shear deformation. This is the shear deformation in green. And this is the shear deformation calculated by the program that can handle bearing capacity and shear, but cannot handle ejecta. And so actually getting the wrong answer is the right answer. So remember that when you're doing an analysis. If you're doing an analysis with a program that cannot capture a mechanism, and that mechanism is important, make sure you don't get a match with the total answer. This is one of the cases that we use to calibrate the Bray and Macedo liquefaction-induced building settlement procedure, and that procedure is only possible because of the case histories that give us confidence that this method can work. So in conclusion, well-documented case histories, especially in geotechnical engineering, advance our understanding, but important in structural, environmental, and other areas as well. Gear and these kind of things have always got to be grassroots. You cannot have an upper leadership telling people where to go. You got to listen to the masses and follow them as they lead. Because so many of the great innovations I talked about today were individual gear members getting together and go, I think this is a better way of doing it. But you have to have standards that you get together and say, okay, well, this is a new technology, but here's how we're going to implement it. Google Earth allows me, like before I had gone to that area, I've been to Santiago, but I had not been to Concepcion, which is an area of major damage. I walked the ground virtually when I was at home. When I got there, it wasn't the first time I'd been there. I'd been there virtually. Remote sensing, LiDAR, structure for motion, they're so important for capturing these things. But it's critical that we systematically, every photograph, every map should have geocoded. It has to have the GPS in the coordinate. You have to reoccupy it. We gave Rob Cahan, who had gone around earthquakes, to say, I'm going to go back to places where there were earthquakes with ground failure and not ground failure, and I'm going to do shear wave velocity measurements. So I can develop a shear wave velocity based liquefaction method. He did a study on past earthquake reconnaissances and realized liquefaction happened somewhere, but he had no idea where it happened. So it's critical that you not only put the GPS coordinates in there and the time and the date, but you put a reference to where it is so that people can reoccupy that site so that you can continue to learn from it. It also makes it effective for documenting, sharing, and archiving. And then last but not least, I hope I've convinced you that many of the things that we do, not just in earthquake engineering, but also run out of landslides and storm surge effects, it's reconnaissance of these field observations that then lead to these design methods that we use today and we're going to continue to use for the foreseeable future. Thank you.